In this video lecture, we're going to go over Chapter 17, Practice Exercise 12. So it says a solution consists of 0.050 molar magnesium and 0.020 molar copper 2+ ions. Which ion will precipitate first as hydroxide is added to the solution? And what concentration of hydroxide is necessary to begin the precipitation of each solution? So what is going on here? What we have a beaker. And in this case, we're told, we don't know the total volume, but you're given the molarity. So I know in whatever volume it is, doesn't really matter, I have 0.050 molar magnesium and 0.020 molar copper. And then what I'm going to do, I'm going to add hydroxide to the solution. And what's going to happen, I will then form some magnesium hydroxide. And I know my KSP reaction is forming the cation and 2 hydroxide polyatomic anions. KSP is then magnesium times hydroxide, remember this time squared. And we're told that numerical value is 1.8 times 10 to the negative 11th. I also know that my copper will form copper 2 hydroxide. So my KSP reaction is copper 2+ plus 2 hydroxide. So the KSP expression, copper times hydroxide squared, and I'm given that numerical value for KSP, 4.8 times 10 to the negative 20th. So right away I can tell, because this K value is smaller than this, the smaller the K value, the less soluble the compound. That means that copper 2 hydroxide is less soluble than magnesium hydroxide in water. However, so if the two molarities were the same, I would just say copper is going to precipitate first. Copper 2 hydroxide will precipitate first because it's less soluble. However, the molarity is smaller than magnesium. So if this is small enough, the magnesium will actually precipitate first. So we're going to have to do the math. What math will we do? We're going to go ahead and solve for the hydroxide molarity for each of these individual ions that is in equilibrium with the solid. So let's look at magnesium first. So I'll rewrite my KSP reaction for magnesium. KSP equals magnesium 2+ times hydroxide squared. I'm going to rearrange to solve for hydroxide, so I can say hydroxide equals KSP over magnesium. And take the 1/2 power, or the square root. Now do the same thing for the copper. So I'll just do the algebra here. Hydroxide equals KSP over copper 2+ to the square root, or the 1/2 power. So let's solve for magnesium hydroxide. My KSP, 1.8 times 10 to the negative 11th, divided by the magnesium molarity that is given as 0.050, and take the square root of that. So my hydroxide molarity for the magnesium is 1.9 times 10 to the negative 5th molarity. So make sure you can get that on your calculator. And for the copper 2 hydroxide, the KSP is given as 4.8 times 10 to the negative 20th, divided by the copper that in this problem, 0.020, and the square root of that. And I end up with 1.5 times 10 to the negative 9th molar. So what does this mean? So this number, 1.9 times 10 to the negative 5th, that means that if I have a 0.050 molar solution of magnesium, I've got 1.9 times 10 to the negative 5th molar hydroxide dissolved. if I have a 0.020 molar solution of copper 2 plus, I've got 1.5 times 10 to the negative ninth molarity of hydroxide dissolved. So the smaller molarity tells you the compound that is less soluble. So what that means because this number is smaller, copper 2 hydroxide will precipitate first. Because less hydroxide can be dissolved aqueous. So copper 2 hydroxide will precipitate first. The molarity of the hydroxide necessary for precipitation is 1.5 times 10 to the negative ninth. For the magnesium to cause precipitation, I need to have a larger molarity of hydroxide, 1.9 times 10 to the negative fifth. So that answers which ion will precipitate first. I know that's going to be my copper. And what concentration of hydroxide is necessary to begin precipitation for each cation. Again, 1.9 times 10 to the negative fifth molarity will cause the magnesium to precipitate. 1.5 times 10 to the negative ninth molarity will cause the copper to precipitate. Okay, and the last slide for this chapter, selective precipitation of ions. And this is exactly what we were doing in lab before our break. And we're going to see this also in Beyond Labs. You'll be doing this as well. So because of solubility differences, if you're starting with a whole group of ions, if we add HCl, anything that is insoluble with chloride will precipitate out, right? And then we can centrifuge, decant the remaining ions. So through selective precipitation, you can separate and identify different ions in a mixture. And again, this is exactly like what we did in lab.